All right, Honors Chem. Today we are going to talk about electrolysis. Okay, so electrolysis is essentially the opposite of a galvanic or a voltaic cell. So instead of having the cell run spontaneously, we actually have to hook this cell up to some kind of a power source to get the electrons to actually be pushed in the opposite way that they would spontaneously go. So electrolysis is the use of electrical energy to bring about a chemical reaction. So we're using electrical energy to bring out a chemical reaction. An electrochemical cell in which electrolysis occurs is called an electrolytic cell. So anything that's labeled electrolytic is going to be a non-spontaneous cell. A voltaic or a galvanic cell would be spontaneous. For example, when a battery is recharged, so when we recharge our phones at night and we plug them in, we are actually running this battery as an electrolytic cell. We're forcing everything back to the starting point to make it fully charged again. Okay? So when the battery is recharged, it's acting as an electrolytic cell. So we've talked a little bit about voltaic cells. So in our voltaic cell first example, we had zinc acting as the anode, and we had the electrons flowing from that zinc. So the zinc plus 2 was being dissolved into solution. So this zinc is losing mass. And as the electrons travel down here, we have the electrons coming to the copper, and we have copper plus 2 in solution. And as the electrons get near the copper plus 2, that plates onto this copper electrode, which is acting as the cathode because oxidation is happening here. So this copper electrode is actually gaining mass. Okay, so that is a spontaneous reaction. When we look at what is going on, we have copper plus 2 electrons giving me solid copper. That gives me 1.342 volts. And if I look at zinc, going to zinc plus 2 electrons, that gives me, that's not plus 1 point, it's 0.32. That gives me plus 0.762 volts. So when I add that all up together, I get about 1.1 volts. And because that voltage is positive, I know it's spontaneous. But the thing is, if I let this go forever, if this zinc is losing mass, eventually that zinc bar, that zinc electrode will be gone. And eventually the copper plus 2 ions in solution will all be used up. So how do I get so that I can use this battery again? I have to recharge it. And in order to recharge it, I have to hook it up to a power source. And that could be a battery or the electrical grid or whatever. But notice now that I have it hooked up to a power source, I am running this backwards. The electrons are now going this way. So I have electrons coming down on the zinc and joining with the zinc plus 2 to plate the zinc onto that electrode, that zinc electrode. So this is gaining mass. And because the electrons are leaving the copper, I've got copper plus 2 going into solution. So my copper is losing mass. So guess what? Copper, when we're using it as an electrolytic cell, becomes the anode, because this is where oxidation is happening. And the zinc becomes the cathode, because this is where reduction is happening. So the poles switch. Okay? Now, when we look at what's going on, we have copper going to copper plus 2 electrons. So that would give me a negative 0.342 volts. And I have zinc plus 2 electrons going to solid zinc, and that would give me a negative 0.762 volts. So together, that would give me a negative 1.104 volts. That negative tells me that this is non-spontaneous. Okay, so in order to get that electrolytic cell to actually push those electrons in the non-spontaneous direction, my power source right here has to have more volts. So it has to be greater than 1.104 volts to overcome that resistance. I've got to have a greater voltage than what that reaction is. Okay? Another way that we use electrolytic cells is to plate metals. So here's an example here. So if you've ever been to a really fancy like dinner party, a lot of times you actually use silverware. Now, silverware is awfully expensive to do it. Sterling, so a lot of times it's called plated. So what we would do here is we would have a metal silver anode. So this is made out of silver. And we would hook it up to a battery. And we get the electrons from the silver to travel along through the battery. And they get pushed out in the circuit to this would be like a stainless steel metal object. It's a fork for this example. So if we have the electrons leaving that silver, we get silver plus ions in solution. And as the electrons come down this stainless steel, they join with that silver plus ion and they plate that silver onto the stainless steel. So we get a thin layer of silver plating all over that stainless steel as the electrons flow into that stainless steel. Now that allows us to have silver, gold. Sometimes they use this with chrome. This allows us to have those finishes without making the whole object out of those precious metals. One, so that we're not using so much of the precious metals, so it's not nearly as expensive. And let's be honest, some of the precious metals like gold and silver are actually quite soft, and they are not durable enough to be knives and forks and spoons. They bend and they'd be soft. Okay, so that allows us to have a core of stainless steel that's a little bit more rigid, a little bit more tough. So it will last longer. Okay, so we can also do this to purify metals. So if you ever go out to Kennecott Copper or a metal refinery, they will actually use electrolysis to get the impurities out of the metal that they have smelted from the ore. And if they can do a series of electrolysis processes, they can get that metal purity to be about 99.999% pure. So it enables us to purify our metals as well. Okay, so let's do some definitions. Now, some of these definitions you will see in physics as well, but we're going to use them here in chemistry. So our first definition we want to do is a coulomb. Okay, so a coulomb is 1 amp or 1 ampere times second. So if we want to think about a coulomb is a measurement of charges, how many charges we have. So this actually equals 6.242 times 10 to the 18 fundamental charges. So that would be, that would be a lot of charges going through per second. Okay. Now an ampere is actually 1 coulomb per second. Okay. So an ampere is about measuring how many charges we have going through an electrical circuit per second. So it tells us how strong that electrical current is. Okay. Sometimes we call amperes amps. Okay. And then we have volt, which is what you're probably used to. You need a 9-volt battery, right? Or there's 120 volts in the electrical circuitry here in the United States. Okay. So volts are joules per coulomb. So energy per coulomb. If we break it down into fundamental units, it's kilogram times meter squared all over amp all over seconds cubed. Okay? It's really the electrical potential between 2 points of a conducting wire. So if I look at the electricity on one point of the wire and the electricity on the other point of the wire, how big is the potential between those 2 points on that circuit or on that wire? As you can probably tell, volt was also named after Alessandro Volta, just like a voltaic cell was. Okay? So let's learn how we do this. We're also going to be using Michael Faraday's. You might have heard of him as well. Faraday cages are really interesting. Michael Faraday experimentally determined that we have 96,485 coulombs for 1 mole of electrons. Okay? So we're going to use all of these different units to help us understand some mathematical problems here. Okay? So here we go. Example number 5. How many grams of sodium would need to be produced at a cathode if 5.5 amps is passed through liquid sodium chloride for 30 minutes? So let's think about what it takes to make sodium from sodium chloride. Now the sodium in sodium chloride is an Na plus ion. Hopefully you agree with that. Now if we have liquid, wow, my computer really just doesn't want to do things. Now, if we have liquid sodium, because if it's hot enough to melt sodium chloride, it's going to be hot enough to melt sodium metal. So if we have sodium metal liquid, what do I have to add to that sodium ion to get it to be a sodium atom? I have to add an electron. So we're going to use this ratio. I have 1 electron for every 1 mole of sodium. Okay, so it helps to write out the equation first. Okay, and you'll notice that we have electrons being added to it. So this is the reduction end. So this is going to happen at the cathode. Okay, so here we go. I'm going to start with my 30 minutes. So I've got 30 minutes. But my amps are coulombs per second. So I need to get my minutes into seconds. So for 1 minute, I have 60 seconds. So my minutes cancel out. And then my amp is coulombs per second. So I can say that I have 5.5 coulombs per second, right? And I want my seconds to cancel. So I'm going to put my seconds on the bottom. So I have 5.5 coulombs per second. Next, I'm going to use Faraday's constant here. So I have 96,485 coulombs for 1 mole of electrons. So my coulombs cancel. And then I'm going to use this relationship. I have 1 mole of electrons for 1 mole of sodium. So 1 mole of electrons will give me 1 mole of sodium. So my moles cancel out. But I want grams. And we know how to convert from grams to moles. So if I look at my periodic table, 1 mole of sodium is 22.99 grams of sodium. Okay? So when I do my calculations, I only have 2 sig figs here. So this will give me 2.4 grams of sodium that I can create off of this cathode being run for 30 minutes. Okay? Now the second part of this problem is how many grams of chlorine will be produced using the same current for the same length of time. And the chlorine will be coming off the anode. And let's write that relationship. So if I have chloride, right, this is chloride, how do I get it to make chlorine? Obviously, I'm going to need 2 chloride ions, but I'm going to need to have 2 electrons coming off of that. That is why it's the anode, because we are losing electrons here. So I'm going to have this relationship. 1 mole of chlorine uses 2 moles of electrons. So I'm going to start with the same thing. I'm running this thing for 30 minutes. I need to get my minutes into seconds. So 1 minute gives me 60 seconds. So my minutes cancel. I'm still using the same amperes. I have 5.5 amps, so 5.5 coulombs per second. So my seconds cancel. Now I'm going to use Faraday's constant. I have 96,485 coulombs for 1 mole of electrons. So my coulombs cancel out. And then I'm going to use this relationship. I've got 2 moles of electrons giving me 1 mole of chlorine. Okay, so my moles of electrons cancel out. Then I just need to use my molar mass. So each chlorine is 35.45, and I've got 2 of them. So 1 mole of chlorine will net me 70.9 grams of chlorine. Okay, I only have 2 sig figs because of that 5.5 coulombs. So this will give me 3.6 grams of chlorine that I will be able to get. So 3.6 grams of chlorine for 30 minutes. Okay, so let's do this as part 1. I'm going to make another video for part 2, and we'll see you in a few minutes. Thanks.